proceed with the presentation today.
This meeting is being recorded.
Thank you, Tyler. So good morning, everyone, and welcome to our Dryden Monthly Learn More series entitled Confidence and Safety in a Deep Geological Repository, or a DGR. My name is Colleen Brasso, City Special Projects Manager, and I, along with my colleague Tyler Peacock, Economic Development Manager, will be your moderators for this presentation. I would first like to begin by acknowledging with respect that we are meeting virtually in Treaty 3 territory and that the land in which we are gathered is the traditional territory of the Anishinaabe and the Métis people. To begin, we would like to express the city's ongoing commitment to provide our community and stakeholders with access to resources and relevant educational information with respect to the NWMO's Adaptive Phase Management Project. I would like to remind everyone that this session is an extension of the City of Dryden's professional workplace and to respect and conduct ourselves in a professional manner that is expected in such an environment throughout this session. There will be an opportunity following the presentation for questions, and we ask that all questions be addressed through a raised hand or the Q&A forum. We would also like to remind everyone to keep your questions relevant to the topic being addressed this morning. This session will be recorded and contact information provided should you wish to address a question after the session has concluded. I am pleased to introduce our presenters for today's presentation from the Nuclear Waste Management Organization, or NWMO. Our first presenter is Paul Guszewski, Director, Safety and Technical Research. The other following two presenters are Nick Nazarfar, Assistant Engineer, Scientist, Technical Officer, Mining and Repository Engineering. Matthew De Los Santos, Mining and Repository Engineering Section Manager. At this time, I will now turn the meeting over to Paul to proceed with the presentation. Paul?
Good morning. Thank you. Let's see if I can share the screen successfully here. Suggesting that you have it disabled.
Oh. Is it going to work now?
I think I can work now. Let's see. Is that working?
That's good, Paul. We can all see it, I believe. Everyone?
Yeah.
Okay.
I can see it on my end.
Excellent. So let me begin. So again, thank you for the opportunity. I've been working in waste management since 1999 and currently responsible for the group here that does safety assessments and does research into the underlying science that we use to support the safety case. And I'm going to give you a very brief overview of confidence safety for the site that we're looking at in your area, based on information that we've been collecting over the past few years. And let's just see, I can move through the slides here. Yes. All right, so let's start. So when we talk about looking for the site, we've been through this process for many years, and we've been looking for three things in the site: that we're able to be confident that the site is safe, that we can transport the used fuel to the site, and that we can have a partnership with the community. So what I'm going to talk about today, though, is on the technical side with respect to primarily the first bullet, just recognizing that the other activities are also ongoing as well. As we think broadly about what is it that would give us confidence and safety in a site, it's summarized in these 8 bullets. And I'm not going to go through them in detail here. Several of them have actually been things that we've been using for a long time as part of the site selection process. And then there are some additional items brought in here that are really the multiple barrier concept, which is common to any site, but as part of the overall confidence, we bring them all together and how the whole thing performs as a combined system for a particular site. So these are the sorts of things that we've been looking at, and they're described in a bit more detail in the report. I'm just going to highlight some items in this presentation. But before I do that, I just want to be clear that building confidence is a process. We started on the process. We started doing studies in the Revel site area back in 2012. There've been a number of studies that have gone underway there, including 6 deep boreholes to date, plus a variety of other ones. Some of these analyses are still ongoing. There, for example, a variety of rock cores that were put into various laboratories. Some of those analyses will take years. They're still underway. And there's a lot more analyses that we're still planning to do. This schematic here is just to illustrate that point, that what we're looking for, what we're describing right now is our confidence based on what we've seen to date, and our confidence in our ability to, confidence in proceeding with this site. We're not saying we have enough information yet to support a license basis decision, but there is a decision that we are collectively making as to whether we proceed with this site, and do we have enough confidence that is worth making that next step. So that's, when we talk about confidence, we're talking about that point in the process. I'd also say that at this point, much of our confidence is built on the multiple barrier approach. You've seen that presented, of course, in a variety of ways. And this is an internationally accepted approach for management of used fuel. Other countries are following a similar approach. But what's different now, we've always had this multiple barrier concept in mind, but what we have now is evidence of the suitability of the rock at the Revel site from our recent studies. And that understanding is summarized in a confidence and safety report that we released in June of this year. Just kind of a little visual here. This is a picture of a variety of tests, measurements, studies on the geology that are underway or have been done, starting from the borehole, and a little bit more visual or visible testing at the site in the top left picture, to a variety of other tests, some of which are done in laboratories. The bottom two, for example, looking at the properties of the rock and the properties of the pore water and the chemistry. Just to give you a sense that there's a lot more that happens other than the things that you see at the site itself. So what do we learn from these things? Let's start with the big picture. The Revel site itself is within the Canadian Shield, and that's the oldest rock in North America. And the figure on the right is colored by the different types or the different groups of rocks within North America. And the red portion is the Canadian Shield, and that is the oldest rock in North America. It's around 3 billion years old. Now, the site that we're looking at is within a batholith, which is a rock, the magma that intruded into the shield. It's about 2.7 billion years old. So part of this larger Canadian Shield, but a portion within it. What we also found from the drilling is that the rock itself is favorable at the site. Most of the rock core that we found during the drilling was a type of granite referred to as granodiorite tonalite, about 95%. That homogeneity is very helpful for us, and it's a good sign for the characteristics of the rock. Now, this rock type is suitable for hosting a repository. Two pictures here to kind of give a sense. The one on the left is actual rock core from the site. That's a nice intact piece, but I think what you can also get a sense from it, just like looking at it, is the uniformity of that rock along that core. The picture on the right is not from our site. This is from the repository site in Finland. It's not exactly the same, but it's a similar type of rock, and I just included here as an illustration of what we think a repository underground at the Revel site might look like should we proceed at this site. Another important aspect is water. And we look at in the rock for the story that the water in the rock tells us. We were only able to collect water samples at 6 fracture locations at depth in the 6 kilometers of core that we've drilled so far. So that's an indication of the low water content. All the rest of the analyses that we're doing are basically by squeezing the rock to try to squeeze out the little bit of water that's in the pore waters themselves, to understand, to get samples of water that we can then do measurements on, because they will tell us the story of the rock and of the water and the history of that water and its isolation from the surface waters, which are things that we want to see as part of the overall safety story. that analysis is still underway. We're still pulling that story together. But in general, what we're seeing is that as we go deeper, the water samples are consistent with what we would expect for general Canadian Shield conditions. Less water, but also things related to the chemistry of the water, where for example, the amount of sulfur or sulfur-bearing minerals would be low because these are conditions that are favorable for the container durability. Now, there is more site characterization required, and if the site is selected, we plan to do these. But we feel that based on the amount of information we've seen so far, what we're seeing in the rock, that the uncertainties are less about whether the site itself is suitable, the rock is suitable, and more about developing that quantitative understanding of the site that we would need to support the detailed engineering and the license application. At the Revel site, one area that requires more work is basically the shape and the properties of the fractures in the subsurface. And we plan to address this through both further site characterization, but also the very design of the repository is such that we have the ability to optimize the layout of the emplacement rooms during the underground excavation. As we're drilling and excavating into the rock, we can make adjustments based on what we find as we're going through that process. A slide that just briefly talks about some of the future work that we would do at the site. Essentially, it's more of the same. We would need to drill more boreholes. There'd be more tests in the boreholes. A lot more rock core would go out for laboratory analyses. And we have underway right now groundwater monitoring, regional seismic monitoring. There'd probably be additional seismic tests within the boreholes themselves, and a variety of other tests, studies that will go on, not just the geology, but regional information, environmental baseline. A variety of studies would continue as part of the future work. So the conclusion, very briefly, is that based on the assessment results to date, that we're confident that a deep geologic repository could be constructed at the Revel site in a manner that would provide safe long-term management for Canada's nuclear fuel. As you said, there's more work to be done, but the information and the basis for our conference to date is summarized in that technical report that was made public in June and is available on our website. That's a very brief summary. I'd be happy to take questions now, or turn it over to Colleen and see if we want to go through the rest of the presentations and then take questions at the end.
Thank you, Paul. I think we'll continue on and then do questions at the very end. I think that would work. So I'm not sure who's next to present. Would that be Nick or Matthew?
That's right.
Nick?
Yes.
So I could turn it over to Nick. And Nick, if you, oh, he's on it.
Okay, thank you, Paul. Deep geological repository design. A little bit of introduction. So designs are at this time preliminary and related to a generic crystalline geosphere and are not detailed site-specific Revel designs. So these conceptual designs are at the same as the 3D model in the Learn More Center. Currently, we're working on a pre-feasibility level of engineering designs for Revel. Detailed engineering won't begin until after the site selection process is finished, which is when we will tailor the pre-feasibility study designs to the detailed site-specific characteristics. So overview of the items I'll be covering today. So for mining and repository engineering, I will cover an overview of the facility and the key component infrastructure, in-room emplacement concept for the engineered barrier system, the DGR development cycle, and my colleague Matthew will discuss the excavated rock management area and environmental controls. So more specifically, I'll be covering the surface facility layout, the shaft sinking and construction, the underground repository layout, mining cycle and sequence, and I will finish with the in-room emplacement concept. So as you see in this picture, the DGR Deep Geological Repository is comprised of the surface facilities, the 3 shaft components as shown in the blue areas in part A, the services area labeled as B, placement arms, as you can see 4 of them here, part C, and excavated rock management area labeled as D here. So the surface facility footprint area is about 250 acres, and the underground repository footprint is about 1,500 acres. So the overview of the surface facilities is shown here for you, and the site is separated into 2 areas. And that separation is happened with fencing and access gates into balance of site and the protected area. So here we discuss the balance of site facilities. The balance of site area considers general non-nuclear surface facilities required to support staff and operations, including the perimeter fence encircling the full surface facilities footprint, a sealing material compaction plant, where the compacted bentonite buffer boxes and spacer blocks will be fabricated. Here we have concrete batch plant, where concrete and shotcrete used for construction and ground support will be made. Some water management areas for stormwater and service water, as well as water treatment and pumping facilities. Then here we have the admin building. I'll try to show with the laser pen here. So here, this is the admin building. And this area here is garage, warehouse, and this area here is for parking. It's a parking area, basically. So the second portion of the site, the protected area shown in green here, basically includes secured area with controlled access and double security fence. It includes all nuclear related facilities and underground access points, which is comprised of the used fuel packaging plant and supporting facilities, quality control and quality assurance, and also all 3 shafts complexes. It also includes the protected area water management pond, as you see here. Okay, so you might ask how the used fuel handling on site will be like. So basically, initially the trucks are entered the site through base balance of site and protected area security gates and access and fences. And then the used fuel transportation package is received at used fuel packaging plant, shown in the protected area here. Then the used fuel is removed from transportation packages and is placed into the used fuel containers. Then highly compacted bentonite buffer boxes are fabricated at sealing material compaction plant and are then delivered to the used fuel packaging plant. Then those used fuel containers are then loaded into highly compacted buffer boxes and are placed into shielded transfer cask. The shielded transfer cask is then, with highly compacted bentonite buffer box, is then transferred underground via the main shaft hoisting complex via hoist and cage, which is the exclusive conveyance for the transfer underground. So as I mentioned, the main shaft is exclusively used for conveyance of shielded transfer cask with the loaded buffer box underground. If you're interested in the function of the service shaft, it's a multi-purpose hoisting complex that is used for personnel and material via main cage. Also used for excavated rock hoisted to surface using 2 skips. And it's also considered an auxiliary hoist and cage for alternate means of egress.
I'm not sure what happened. Nick, you are muted.
Oh,
Nope, we're good. It didn't stop there, Colleen, on my end.
are we good then?
Yeah, we can hear you, Nick.
Okay, perfect. Okay, and the exhaust ventilation
Hello,
shaft.
Nick. We are having troubles hearing. We're not getting your audio.
Oh, okay.
I'm getting it on my end, Colleen. I don't know if you're having a technical issue on your end, but I am getting him on my end.
I can hear him as well.
Yeah, I can hear him as well too.
Also good.
Okay, thanks everyone for confirming. Can you hear me calling now or?
I'm getting a thumbs up from everybody online too there, Nick, so you can continue.
Okay, perfect, thanks. So the exhaust ventilation shaft is used for basically the third shaft is the exhaust ventilation, and it's used for primarily exhaust airway from underground. It's also considered an auxiliary hoist and cage for alternate means of egress and to facilitate shaft inspections. So shaft sinking and construction. Speaking of the three shafts, so they will have a finished inner diameter of 7 meters, which is the open clearance inside of the shaft liner. Head frame will be made of concrete and steel, and it ranges in height from 40 to 60 meters. So if you're wondering how high or tall is that, this would be about 12 to 18-story building. For reference, the eastern white pine tree range in height from 15 to 24 meters. So how shaft sinking and excavation cycle work? Basically, the method designed or recommended is the controlled drill and blast as the process. The picture on the left shows the Galway stage equipment, which would be used, and it's a multi-purpose platform for all sinking activities shown in the picture. And it is also used to lower equipment into the shaft. After drill and blast of the shaft face is completed, then the muck removal with a mucker and bucket winched to surface happens. Then it will followed by ground support as required. Then after that, the geoscience performs their verification. Then we will install the liner, the shaft liner. Then the cycle will restart for each round, basically. The other important topic here is the water control methodology. So the water control methodology that are commonly used in the mining industry include common techniques such as pre-grouting, ground freezing, grout curtains, and installation of hydrostatic liners. So it is manageable to sink shaft through water-bearing zones. There are case studies in potash mines in Saskatchewan done on this, and the shaft is sunk through Blairmore Formation, which is a loose and porous water-bearing formation, sand formation. The water control is achieved primarily using ground freezing techniques and installation of hydrostatic liners. The liner design and shaft sinking water management strategies will be defined once the additional site-specific geotechnical and hydrogeological information becomes available to us. So here, to the right, you see a picture of the generic crystalline underground layout. Let me get the laser here. So this area here is services area, where shafts connecting surface to underground. Also in this area, there's supporting infrastructure and installations, including mobile maintenance shop, water recycling, dewatering, consumables storage, refuge stations, and so forth. So these 4 placement arms, they include a twin access tunnel to each placement arm, with placement rooms developed to either side. Using an adaptive layout and approach will allow for higher flexibility to adjust to geosphere information as it is identified. Just note that designs will change as we receive more borehole data in the future. So drill and blast cycle, as we discussed briefly before, so it's a controlled drill and blast that is currently assumed for the excavation of all the lateral development. So this is a very mature and efficient technology used widely in the mining industry. It is flexible and can be adapted to a range of rock conditions and tunnel shapes and profiles as required. The controlled drill and blast will focus on minimizing damage to the host rock during excavation by limiting the amount of explosives detonated at the same time, which lead to reduced resulted vibration. So we're also considering a fully battery electric underground mobile equipment fleet for all activities to minimize carbon footprint. The detailed steps of the drill and blast cycle includes drilling of the face as the first step, including closely spaced perimeter hole. Load those perimeter holes with explosives and blast them. Then we ventilate, blast gases, and the broken rock will be removed via LHD or load haul dump equipment, and underground trucks will haul those to the service shaft loading pockets. Then the installation of ground support happens, and geological and surveying mapping will be carried out. So the new development in mechanical excavation technologies will be monitored for applications in hard rock. So this may be considered as an alternative as the technology mature. So here I have a video. So the construction sequence for the major development activities are modeled and scheduled in a mine planning software called DESWIC. So the color coding of the placement arms are only to denote different panels, and they're not to indicate the difference in terms of construction, operation, or quality. So, okay, let me see. So video is a bit tricky, but I try my best to make it work here. So as the first step, as you see here, the shaft sinking of the exhaust ventilation shaft and the service shaft occur. And as a second step, those two shafts are connecting via underground lateral development of the services area. And you see on top here, the main shaft sinking also happens, and the development of remaining sections of the services area and primary infrastructure. So as the fourth step, the access tunnels for each arm, as well as the first and last placement rooms in each panel to assist with geoscience verification activities will occur. Once the first full panel is developed, transition to operations with placement activities and development of placement rooms in a separate placement arm will occur concurrently.
So Nick, there's a question in the chat in the Q&A box at the bottom of your screen. I don't know if you can see the Q&A box, but the question is coming from Bernane Lloyd. She said on the slide titled shaft sinking, you listed freezer walls as a common mining technique. Is this an option NWMO is considering for a DGR at the Revel site?
Yeah, sure. I'm not sure, Colleen, if you want to take that to the end or just to be consistent with all the questions.
We can answer that at the end if you'd like. That's
Okay,
fine.
let me just go back.
Just to keep you aware.
Okay, sure. Good to know. Okay, I'll continue and then we will for sure address all the questions at the end. Yeah, so basically, as you see in the video, that's the step number 4. And step number 5 is once placement is complete, 70-year extended monitoring period followed up with decommissioning and closure will occur. So what do we mean by placement activities? What does the emplacement look like? So basically, as you see in the visual here, you can see the emplacement concept. So let me get the laser again. So these are basically the highly compacted buffer boxes loaded with the used fuel container. And the grayish ones, the dark grayish ones are the spacer blocks, also using highly compacted bentonite material. And this material, there's material encircling the buffer boxes is the gap fill material. So the placement rooms are quite narrow. So as you see here, they're 2.4 meter high, 3.2 meter wide, but they're rather long, around 300 meter in total length. Once the first full of panel of placement rooms is excavated, placement activities can begin, including loading the buffer boxes and spacer blocks placed in a staggered pattern. Then the gap fill, as you see here, gap fill material placed around the compacted boxes will be the step after. As you see here, the cycle is repeated until the room is completely full and the placement room seal is constructed afterwards. But earlier this year, a proof testing program was completed at NWMO Oakville facility, focusing on the production of used fuel containers, bentonite buffer boxes, and placement and compaction of the gap fill material around the buffer boxes in the market placement emplacement rooms. So some photos from the facility, and I'll start in a clockwise direction from top left here. That's the bentonite buffer boxes with some gap fill material placed around the perimeter. So this picture is a vacuum lift for the floor blocks. This one here is a placement equipment carrying a bentonite buffer box. This one here is a gap fill placement and compaction equipment in the mock placement room. And the last one is the outer view of the mock placement room. So in summary, basically we touch based an overview of the surface facilities and used fuels life cycle management from receipt on site to underground emplacement. We also talked about shaft sinking with water management techniques and technologies. And we also touch based on underground lateral development sequences and phases over the life cycle of the repository. So yeah, that's it for me. I'll now hand it off to my colleague Matthew for the next section.
Thanks, Nick. So I will be talking today about our plan for the excavated rock management area. So that consists of the construction and the reclamation, some ongoing work around best management practices for mitigating some of the impacts from construction and operations, and then just an overview of our site water management concept. Next slide. So the excavated rock management area will be required to store the broken rock that's excavated from the deep geological repository during construction and operations. So currently we're looking at about a 500 meter by 500 meter pad size and a total stockpile height of 15 meters. That'll be constructed in 3 5-meter lifts. So preparation for that will be leveling and grading the pad area and then installing an impermeable liner below for runoff management. Then the excavated rock will be transported from the service shaft to the excavated rock management area where it'll be deposited and then shaped with bulldozers. In addition to the construction, we're also planning some water management around the footprint. So we'll have perimeter ditches that'll direct any stormwater runoff to a dedicated stormwater management pond. And then the impermeable liner below will also assist with managing the runoff. Next slide. So reclamation of the excavated rock management area. So reclamation generally, objectives are to protect public health and safety in the long term, alleviate, mitigate, or eliminate environmental damage or impacts associated with the construction, and then to return the land to its original condition or as close as possible or an acceptable alternative. So some of the things that we'll be considering for rehabilitation and reclamation of the excavated rock management area include restoring the surface by revegetating and hydroseeding with plant species that are similar to the area and what was in the area prior to construction. And then the goal is really to ensure that the surface vegetation is capable of supporting itself sort of in a self-sustaining ecosystem over the very long term. So our detailed closure plan will be developed at later stages. We're doing some ongoing chemical analysis of the rock just to make sure that we are designing all of the appropriate and adequate measures in place to manage any of the stormwater runoff. Next slide. So just an example of pre and post reclamation. So this is after construction, revegetating and hydroseeding. In our case, for the Revel site, we'd also be looking at planting trees that are similar to the nearby surroundings. So that's one distinction to the image in the bottom right. Next slide. So in terms of best management practices during construction and operations, we're looking at operational controls primarily, and then some other engineering considerations to try and mitigate some of the impacts. So principally noise and vibration, dust control, and visual impacts. So on the top right, you can see a water truck spraying water. So that's a dust suppression, dust control method for on-site roads and access roads. And in the bottom right, you can see from the South Bruce site, some visual screening berms that have been placed around the borehole sites to minimize some of the visual impact from activities. Next slide. So as Paul mentioned, where we're putting the deep geological repository has favorable chemical composition. There's low groundwater movement, and it's also capable of resisting changes from earthquakes and ice ages. So it's part of what's guiding the repository depth. Next slide. And in terms of site water management, we're considering currently that there will be inflow from 3 primary sources. So there will be raw water that's sourced as makeup water for use in the streams. We'll have stormwater or rainwater that's collected on site. And then although we are expecting minimal water inflows from the DGR or from the repository horizon, as Paul mentioned, we will be designing in the capacity to deal with any water inflows and then recycling that water as much as possible for reuse in the underground service water stream. So once this water is collected from all three of these sources. It'll be monitored and treated as required for use in our different streams. So we have surface water that's used for facilities and operations, both on surface and underground. We have domestic or potable water that's used for drinking and kitchen sanitation facilities. And then we'll also have fire water that's used for fire suppression on site. So once all of this water is used in each of these streams, it'll be collected and then treated and monitored. We are looking at recycling water for use as service water where possible, and also ensuring that any water or excess water that flows off site is monitored and treated to ensure that we're meeting all regulatory requirements before any effluents transferred off site. Next slide. So a couple of technologies that we're considering. So from left to right, we have HEPA filters that we're using or planning to use on the ventilation stacks for the used fuel packaging plant and the exhaust ventilation shaft. In the center, we have an example of an effluent monitoring station and water quality monitoring station for a pond. So we'll be employing several of those for managing effluent on site. And the ponds will be capable of retaining any water if the monitoring flags if there's any material contained that exceeds quality limits, where it can be then pumped out or redirected to the water treatment plant for additional treatment. And in the top right is just an example of a modular water treatment system that we could use as an example for some of the water treatment on site. In addition to these, as Nick mentioned, we'll be looking at shaft liner designs and water control methods for the shaft sinking and construction and long-term water management. And all of our systems on site will have built-in redundancy to ensure fail-safe. So that's pumps, filters, piping, treatment plants, etc., and monitoring. Next slide. So in summary, breeze through that one a little quickly, but we discussed the excavated rock management area, construction, and reclamation, and that'll be used to store all of the excess rock that's excavated from the underground repository. We'll be reclaiming it with plant species that are aesthetically similar and similar species to the surroundings, and ensuring that it's capable of self-sustaining that ecosystem in the long term. And then our site water systems, which we're currently designing, are being designed to recycle water where possible, and ensuring that we're treating and monitoring any water that's flowing from the site and ensuring that we're meeting regulatory requirements. Next slide. And that's it for me. So I guess it's just time for questions now. Thanks.
Okay, great. So we have some questions in the Q&A, and I've marked them as that we'd like to answer them live here. So I'm gonna jump back to Nick really quick on Bernane's question. So Nick, can you see the question in the Q&A box? Sorry, you're on mute there, bud.
Okay, so the first one here, 11:30 a.m.
Yep.
Okay, sure. Yeah, so the question is on the slide titled shaft sinking, freeze-up walls as a common mining technique is listed. Is this an option NWMO is considering for a DGR at the Revel site? Matthew, would you like to take that one?
Sure, I can take a stab at that one. So the examples that Nick provided in the presentation are available technologies that are used in the industry. Based on the drilling results so far, we're not expecting water inflows nearly as high as what they see in Saskatchewan and the Blairmore. That's more of an upper end case. So we will be considering industry best practice grouting options and shaft liner designs to address water inflows, and that'll be dependent on some of the additional hydrogeological information that we receive from the drill programs.
Thanks, Matthew. Next question is from our Mayor Jack Harrison. do we have the seismic technology to determine whether the fractures are below 200 meters in the placement area, or do we have to rely on assumptions and avoidance when encountered during the creation of the deep placement area?
Paul?
Yep, I'm coming online here, just going to speak to that. So it's a combination of things. For example, we're aware of some of the larger fractures because they intercept the surface, so we know something about those. The boreholes themselves will be designed to then look for the larger features. Seismics, both from the surface as well as from the boreholes, gives us information. As we look at the rock and the pore water, that there's some information we can learn from that. And then the final steps is, as we go underground, we get the final confirmation. But even there's two phases. If you recall from Nick's presentation, they showed the excavation, first of all, of the access tunnels and pilot holes around that. So that really tests out a given panel area before we actually start excavate rooms in that. And then finally, we have, as we're excavating the rooms themselves, before we choose to put any containers in them. So it's a combination of all of these that we would be using to provide confidence in the location of the key fractures.
Okay. Next question is from John Dove. So what is the risk that all the shaft and tunnel development will destabilize the rock formation?
I can take a stab at that one. So based on the geoscientific drilling results to date, the rock is very good quality. So there's no expectation that it would destabilize, and we'll have all required ground support measures as part of our design process.
Thank you. Can any of the excavated rock be used as backfill, or will it be too porous?
So we haven't detailed out the requirements on the backfill for the decommissioning enclosure. That's to be investigated, but it's a possibility.
Next question, are you planning on capping the ERMA with soil? Will be difficult to grow anything on the waste rock material? If so, where would the capping material come from?
So we are planning on revegetating the excavated rock management area as part of the rehabilitation and reclamation. We haven't done the detail yet in terms of the requirements or which species or where the capping material would be sourced.
Okay. And Wendy asks, the water cycle was unclear to me. Is water that is drawn up from the DGR treated separately?
So currently, so that was a very simplified flow diagram. The current concept is to recycle water underground as much as possible and reintroduce it into the surface water stream. And then water that is drawn up to surface would join the rest of the surface water treatment process.
And that's all the questions that we had listed in the Q&A. If anyone wants to ask a question live, please raise your hand and you'll be allowed to unmute and ask your question. I don't see any popping up here, folks, but I will turn the meeting back over to Colleen to wrap us up.
Thank you, everyone. I great questions and participation. And I just, in closing, would like to encourage everyone to subscribe to the city's webpage to be apprised of ongoing updates and access to information and resources, and to view recordings of this session as well as past sessions. You can refer to the link, and Tyler, if you could post the link for our webpage in the chat, that would be great. And should you have further questions that following this presentation, you can direct them to my contact information on that webpage, or you can email me at cbrasso@dryden.ca.
Colleen,
yes,
there has been a couple more questions that have been popped in here.
Okay,
So,
I'll just hand it over to Tyler then.
Yeah. So Bernane asks, Nick mentioned a shielded transfer cask. Is that the same as the UFC/buffer box transfer cask referenced in the September 2021 conceptual design report?
So basically, a shielded transfer cask is an equipment that provides shielding for the used fuel container during the transfer from UFBP to the placement room. But for further details, I'll pass it to Matthew for this terminology.
So the shielded transfer cask, UFC buffer box transfer cask, I believe those are the same, yes, as what was described in the conceptual design report.
Next question, does the confidence in safety report integrate findings from all 6 boreholes? And I think we're just referring to, at this point, the Revel site.
It does not. It was essentially based on information that was available the beginning of the year, and we didn't have all those results yet. But I'd say actually based, however, on the results that we've seen since then, they're still consistent with the story that was presented when that report was written.
Thank you. Which 3 boreholes will be used to monitor pressure? There's a reference page 65 in the confidence report.
That's a geoscience question. I'm not sure which of the 6 are currently being used to monitor pressure. We'd have to get back to you on that one.
Thanks, Paul. If you could do that for us, we'll happily post the answer to the question on the website. And last question here from Bernane. Where are the results from the 6 boreholes available?
I'd just say generally those reports are still in preparation, so they've not been released yet.
All right. Yeah, and obviously when they are released, we'll be able to have access to them through the NWMO's website.
I'm sure they'd be shared with the community as well, yes.
Thank you, Paul. Okay, Colleen, that's all the questions we have for now.
Okay, thank you. And the one question that we'll get an answer to that from the NWMO, we'll also post that on our webpage and make sure that you have that available to you too. And just to close, I'd like to thank everyone for attending. A reminder that we will post the recording on our webpage, and as well as any of the questions that weren't answered, and we'll post that as soon as we get the information. And I'd like to thank everyone for participating today. Thank you.
Bye, everyone.
Thank you.
Bye-bye.
Bye-bye.
Thanks, everyone.